Okay, so this lesson module is on two specific topics, kinetics and equilibrium. Now you could spend days and days on each one of these topics. We're going to only cover it in a few minutes. So kinetics is basically associated with motion, and in our particular case, it's associated with the movement of particles in a reaction to have the reaction work. Okay, so our definition of kinetics for chemistry will be how fast, the rate-wise, a chemical reaction transforms reactants into products. It's a relative term, so fast in one case would be slow in another. So for example, stainless steel rusting is a very slow process compared to mixing vinegar acetic acid with baking soda, sodium bicarbonate. That's a very fast reaction. And you've seen that in the lab. When you mix baking soda and vinegar, you get a quick instant bubbling. And the reaction rates can change dramatically during a chemical reaction. So we'll talk a little bit about that in a minute. And there are many factors that will affect the chemical rate of reaction. How many can you think of right now? Okay, so before we get into the things that will affect the rate of chemical reactions, we have to understand how a chemical reaction works. We've talked about this mixing A and B, and you get C and D, but really what's going on the molecular or the atomic level? For a chemical reaction to occur, the reactants must be able to collide into each other with the proper orientation. I'll talk about that in a second. Bonds then must break, the atoms must rearrange, and then new bonds form. And then the products must move away. So any activities or actions that change the rate of each of these can affect the rate of reaction. Okay, so to get a reaction to start, you've got to be able to get those molecules or those reactants to collide with each other in an efficient manner so that they are orientated in the proper way and they can then reassemble into new materials, the products, right? In order to do that, you've got to add energy to do that, to get those molecules to move around a lot. So that's called the activation energy. That's the energy you need to get the reaction to start, get those collisions to start really going at each other. So the activation energy is just the measure of how much energy you need to get the reaction to start. And if you look at your little diagram here, down here, it's the energy you needed to go from wherever you start with, which is the reactants here, to the products. How much energy do I need to get over the hump? And that's my activation energy. And in this case, it's pretty high. It's 200 kilojoules. In this case, it's much lower. It's 60 kilojoules. All right, and those are my products and my reactants. That's the energy of my reactants versus the energy of my products. Now we're not going to do a lot about those curves. Just signifying that the bigger the hump is, the higher the activation energy. The higher the activation energy is, the harder to get the reaction to start. Now it's like a roller coaster, right? When you want to go on a big roller coaster, you start at the ground level and then you hoist that car up with all those people in there. It takes a lot of energy to get the car all the way to the top, let's say 200 or 300 feet in the air, right? That's a lot of energy to get all that people up there. Let's say the roller coaster was a smaller roller coaster and only was 60 feet in the air. That's a lot less energy to do, and therefore it's easier to get that roller coaster to start. You need a bigger motor on the first one, maybe bigger motor on the second one. Okay, so this list here is not exhaustive. In other words, it's not complete, but it's the main ways that we can increase the reaction rate of a particular reaction. So one way is to increase the temperature. More temp means higher energy per the collisions and more collisions per unit time. Increase the concentration. When you put more particles in a volume, there's a lot more collisions per unit time. More collisions means higher reaction rate. Increase the surface area. By increasing the surface area of something, you have more sites in order for the reaction to take place. So think of it this way. If you took a big block of sugar and you try to dissolve it, it takes a long time. But if you ground that sugar up into very, very fine pieces or grains and then dumped it into the water, it dissolves much quicker. Very similar to a reaction. Add a catalyst. A catalyst lowers the activation energy. Now there's a mechanism for doing that where we're not going to get into, but adding a catalyst will lower the activation energy. Lower activation energy means it's easier to get that reaction to start. Mix and stir it. Mixing decreases the travel distance between reactants. Remember, we got two unreacted materials, and if they have to find each other and travel long distance, that's going to take a while for it to react. But if we add some stirring motion in there and get those particles to fly past each other a lot more frequently, eventually they're going to collide. And then do the reaction in a solvent. A solvent basically dissolves the material into the smallest particles it can, either in ions or just molecular level. And those are more apt to react quickly than if it's left in a bulk state. Okay, so that's pretty much what we're going to talk about is reaction rates. We're not going to calculate reaction rates or do any of that stuff. Just what are things that increase the reaction rate, what do we mean by activation energy, and what do we mean by kinetics? So generally when you mention kinetics, you also talk about equilibrium. Equilibrium is a state in which the forward reaction and the reverse reaction are going at the same rate. And what do I mean by that? What do you mean by reverse reaction? Well, we'll talk about that in a second. Okay, so let's try to make this as simple as possible. Equilibrium is defined as when the forward reaction of a chemical equation is equal to the reverse reaction of the chemical equation. Now you may be saying, what do you mean by reverse chemical reaction? Well, here's the thing. When we talk about chemical reactions, we've always assumed that they're 100% complete. In other words, when we mix A and B, all of the A and all of B go to C and D. And that's not the case. What's really happening is when you mix A and B, you're going to make some C and D, and then some of that C and D is going to go back and make some A and B. And that A and B is going to then go back and make C and D. And it's going to be a forward and back process all the time. It's kind of like hitting a tennis ball to your partner. You hit the ball making products, and the ball comes back as reactants. You hit it back as products, the ball comes back as reactants. Another analogy would be like this, for as far as the rate. You're trying to dig a hole, and your dog is pushing the dirt back into the hole while you're trying to dig. The faster you dig, the faster the dog puts the dirt back in the hole. So the size of the hole is not changing, but you are still moving dirt back and forth into the hole. It's just coming in and going out at the same rate. Okay, so if you look at this little graph here, we start out with 100% reactants, and then over time we get products, and then we start out with no products, and then sometime we get at some level. But at the end of the day, the equilibrium rate says that the forward reaction this way is equal to the reverse reaction this way. As fast as I'm making HI, I'm decomposing it into H2 plus I2. And that defines equilibrium. So when the rates are equal, going forward and back, at the end of the day, the change in concentration of the product and reactant does not change. Okay, so real basic, we don't have a lot of time to get into calculations of the equilibrium concentration based on concentration, but here's the general high-level definition. The equation is the equilibrium constant, K, is equal to the concentration of the products over the concentration of the reactants. Now, the equilibrium constant tells you a bunch of things about the reaction. It can tell you which side of the reaction is favored. If K is much greater than 1, then products are favored because there's more products than reactants. So the concentration of the products divided by the concentration of the reactants, if that's greater than 1, then the products are favored. If the concentration value is 1, or very close to 1, then we roughly have equal concentrations of products and reactants. If the concentration is less than 1, that means that the product concentration is less than the reactant concentration. Therefore, we have favored reactants. So less than 1, favored reactants. Greater than 1, favors products. Roughly equal or equal, they're both the same. Now, what happens when you get K to be very, very small, much, much less than 1? Then you can consider that to be a reaction that really doesn't go, right? Because you're not making any products at a rate that's significant, right? So it would be kind of what is the equilibrium constant of this reaction? If it's, let's say, 0.0001, you can say, well, if I mix those two together, I'm not going to get a lot of product. I'm still going to have a bunch of reactants in my vessel. So understanding what the equilibrium constant is can tell you whether or not the reaction is favored or unfavored. Okay, when we talk about equilibrium, we're assuming that the equilibrium is a steady state, right? Now, what happens when we do something to the process or the system that has this equilibrium in it and we change it? So we change temperature, or we change the pressure, or we change the concentration of one or more of the reactants. What does that do to the equilibrium? Well, here's what's cool about it is there's a way to predict what's going to happen, and that's Le Chatelier's principle. Now, we're not going to get into too much details on this, or we're not going to do any real calculations on this, but you have to be kind of aware of that you can shift the equilibrium in a chemical reaction and use that shift to your advantage, and I'll give you an example of that in a minute. All right. So what do we mean by stress a system? Well, we can change the temperature. We can change the pressure, which is only going to really affect gases, because if you change the pressure in a solid or a liquid, it doesn't really affect anything. And we're going to increase or decrease the concentration of the reactants or products. Okay? So let's see what that means on the next page when we talk about, well, what happens when we shift these? What does that do to the equilibrium? Where does the shift get taken up by? Or how does the system offset the shift? Okay, so we're going to talk about equilibrium seesaw. So basically this will explain Le Chatelier's principle. Think back to when you were a kid. Did you ever go to the park and play on the seesaw, right? So you always found a kid that was about your side to balance the seesaw out, right? If you ever played with somebody who was much heavier than you are or much lighter than you are, the seesaw didn't work that well, right? So when I used to play and I go there, if I ever tried to play with my mom or dad, this is what would happen, right? I would get on the seesaw, and then they would get on the seesaw, and the seesaw would do something like this, right? And this would be my dad, and this would be me, and the seesaw wouldn't work that well, right? I would try to push down, and I couldn't. My dad would push up, and all of a sudden he'd get close to halfway. Like he would push up, and he would get close to halfway, and then he'd come right back down, right? So what would my dad have to do? He'd have to do this. He'd have to slide towards the middle to change the balance point. And when he did that, then it was easier to teeter-totter. As he slid in the middle, now this started to move up and this started to move down, and we got more uniform teeter-tottering. Okay? Same thing happens when we talk about chemical reactions. Okay, so let's look at a chemical reaction, and I put A and B on each side now. AB on the reactant side and CD on the product. So let's say we add A. So we're going to add A. So let's put another big A right here. So we're going to add some A. And then what's that going to do to the teeter-totter? Well, I hope you can see that the teeter-totter now is going to shift in this direction. Okay, and when it does that, now we have, relative to C and D, we have a lot more A and B. So what's going to happen is that's going to convert into C plus D, more C plus D. And when it does that, what's going to happen is this is going to decrease eventually, and this will increase, and the teeter-totter will now come down on this side and come up on this side and level out more. So the expression is add, the shift is away. All right, so here we go. We're adding to this side, we're shifting away towards the reactants, the product side, right? If we did the same thing on this side, it would just be the other way. Okay? All right, so let's look at the next one. Okay, so let's now look at one where we take, let's say we're making we put A and B in a reactor and we're making C and D, and we really want to maximize the amount of C and D we're making, and we need it quick. So what we're going to do is, as we make C and D, we are going to remove it. So we're going to remove C, so we're not going to put it here anymore, we're going to put it up here. So as we make C, we're going to take it out right as soon as we get it, right? So what's going to happen to the fulcrum, right? As we remove C, the fulcrum is going to lift up like this. Why? Because we have less C and D on the product side. Remember, we're taking C out of the system. It's no longer in the system. So this is going away out of the system. So it doesn't balance on this part anymore. So this is going to become heavier. And so what has to happen? Well, something has to happen, and what's going to happen is this material here is going to shift and start making more C, because as we pull C off, the reaction wants to have C at equilibrium, but we keep removing it. So the equilibrium is shifting. So it's we're taking away, and then we're going towards. So take, towards, add, away. That's basically the thing. So look at your seesaw. Which side of your products and reactants, what are you doing? Shifting it away or shifting it towards?